Welcome to a proof of the uncountability of the real numbers, or the set of real numbers. Now, instead of considering the whole of the real numbers, we will only look at this open interval. The interval that contains every real number between 1 and 0, and not 1 and 0 themselves. Now, if you think about it, it makes sense that if you have this interval and it's uncountable, right? It's, I don't know, unc, then this should imply that the real numbers are uncountable because they contain this interval. But actually, it's even the other way around. The uncountability of the real numbers also implies the uncountability of this interval. And the intuition behind this is, if you could count this interval, you would only have to count the intervals after that, and they would basically be countable, like, or at least like whole numbers. So this is the intuition behind this. Okay, now let's go on to our proof by contradiction. This is also called Cantor's diagonal argument. Okay, so assume there is a bijective function f such that f maps every natural number onto some number in this interval. Remember, bijective means the same thing as injective and surjective, or one-to-one and onto, if you've learned it like that. Okay, now let's say for every n out of the, or in the natural numbers, we have a function, and this function, this is the function from above, takes a natural number and maps it onto some number in our interval, such that the number represents the kth digit of the nth real number in decimal representation. Okay, so this is the nth number. We have enumerated them. This is just what we do if we map the natural numbers onto anything. And we have some fourth digit here, right? This is the kth digit, and this is decimal representation. Okay, now we will do this for every number in our interval, and we will need every natural number to do this, right? We have infinite natural numbers and infinite numbers in this interval, and they have this representation, right? And we don't really know, we don't really need to specify how we do this enumeration. Okay, but now that we've done this, we will define some number in this interval and we'll go looking for it. So let's look at this number. It's from this interval. It has this representation. Okay, we will just call the digits b, so to avoid confusion. And we say, well, the nth digit is 7 if the nth digit of the nth number is not 7. And it's 5 if the nth digit of the nth number is indeed 7. Right, so if we have this here, this number for f of 1, then our new number will look like this. And we don't know what comes afterwards. Okay, so now we have to ask ourselves, where do we find this number? Can it be our first number? No, we've just seen this. It isn't the same number because there's a difference in this digit. Okay, then can it be the second number? F2. Nope, it cannot be the second number because there's a difference in the second digit of the second number. And you see, it just goes on. So f of n cannot be the same as the number we've defined here, because it will have a different digit in the nth place. And thus, the theorem is proven. There can't be an I in the natural numbers such that f of I equals x. Okay. The theorem is indeed proved.